Welcome to this video in the periodic table unit. This is 4.3 part 2. In today's video, we are going to once again take a look at how structure dictates properties that we see on the periodic table and delve into our periodic trends. We're going to cover ionic radius, electron affinity, metallic and non-metallic character, and reactivity. If you haven't already done so, please make sure you have your chemistry notebook out, you have your writing utensil at the ready, and we are also going to need our periodic table and our CSERT open to table S. There is a lot of learning to do today, so let's get cooking. The first trend we are going to cover in this video is ionic radius. And you may be saying to yourself, that sounds a lot like the very first trend we did in the other video, atomic radius. But know this, those two things are not the same, but they are related. So what's ionic radius all about? Well, first thing you got to know is ionic radius is going to compare the size of an ion to its parent atom. And the parent atom is the atom that the ion used to be before it gained or lost electrons. And if we go back to the atomic theory unit, you should know a little bit about how ions are formed. Basically, if you're losing electrons like this magnesium that's here, we see it forms a +2 ion, you are going to be a positive ion called a cation, not cation, but it is cation. And obviously, when you gain electrons, like we look at the most common charge of sulfur here, it's a -2, you would be forming a negative ion, which is referred to as an anion. Peeking at this picture that we see here, one thing becomes apparent very quickly. When we look at our metals, the size of the ion, which is here in pink, winds up being smaller than the parent atom is. And conversely, the size of the non-metallic ion is larger than the parent atom used to be. Now that we understand the trend that metals lose electrons and have smaller ionic radii than atomic, and non-metals will gain electrons and therefore have larger ionic radii than atomic, it is time to talk about how structure of the atom dictates this property. And in order to understand ionic radius, you got to know some facts about electrons. So let's throw those at you right now. You should at this point understand that electrons all have a negative charge. And obviously, because all electrons are negatively charged, if you take two electrons and you put them next to one another, there is going to be electron to electron repulsion. What winds up happening is what we have written down here in red, and this is probably one of the most important things that I'm going to talk about in this video, and it is that electrons will want to maximize their distance from each other to minimize this electron to electron repulsion. This means they will drift as far away from one another as possible to minimize the repulsive nature of their charge. The last thing you have to know about electrons is that they are negative and therefore they are attracted to the positive nucleus. So there's a lot going on in the cloud. There is electron to electron repulsion, but yet there still is some attraction to the nucleus. To help us make sense out of why a metal ion is smaller than a metal atom, you have to understand what is happening when that atom is losing the valence electron. And essentially, there is far less electron to electron repulsion. So if we take here the example of these witch hats that we're looking at, I got some leftover guitar parts, pretend that those are electrons in a cloud. And we know that electrons want to maximize their distance to minimize repulsion. So if I were to remove an electron from the cloud, all of a sudden, the size of our cloud shrinks. Why? Well, there's now less electron to electron repulsion, and the nucleus has an easier time attracting those electrons towards it without them pushing back to get further away. If I take out another one, the cloud shrinks even more. If I take out another one, the cloud shrinks even more. So in the end, we are going to find the removal of an electron from the cloud of an atom will reduce the size of the cloud and effectively make the ionic radius smaller than the atomic radius. We are going to find the same principles apply when you are gaining electrons. So when the atom gains that electron, that extra electron in the valence shell is going to add repulsion. Let's take a look at our witch hats that we have here once again for the example. So here I have 5 electrons that I'm looking at, and obviously if we are going to add an electron, it's going to now enter the valence shell. Those electrons are going to be near one another, but they're going to want to maximize distance to minimize repulsion. That made the size of our cloud grow. Let's throw in another electron so it squeezes its way in. Well, now the electrons are going to want to spread out, maximize distance to minimize repulsion. So as that cloud size spreads out, the ionic radius winds up increasing and will certainly be much larger than the atomic radius was. The next periodic trend we're going to talk about is known as electron affinity. And if you are taking Regents chemistry, this is not for you. But if you're an AP or honors, you probably want to tune in and learn a little bit about it. So let's decode what this means. Affinity is a natural liking for someone or something. And anyone who knows me knows I have a natural affinity for bacon and chocolate and snack foods. I absolutely love them. But in chemistry, it's not about snack foods, it is about electron affinity. And so by definition, electron affinity is the change in energy that is going to occur with the addition of an electron. And that change is measured in how many kilojoules are either absorbed or released per mole of electrons. Let's peek at this animation here of an atom acquiring an electron. And you notice as it acquires it, there is energy that is being released. For most elements, what we're going to see is that energy is released when electrons are gained. And you're going to notice we have many negative values for our electron affinities. The greater the negative value, the greater the electron affinity is. So remember, negative values imply exothermic reactions or releases of energy, whereas positive values for energy imply endothermic reactions. So what does the value of an electron affinity tell us? Well, the more negative the electron affinity value, that corresponds to a greater attraction for electrons for one of those atoms. This means now that we have the ability to quantify based on releases and absorptions of energy, how likely something is to gain an electron. So what we'll notice is up at the right-hand corner of the periodic table, we have the largest electron affinities, and at the lower left of the periodic table, we have smaller electron affinities. And that will correspond to what you already know about the periodic table, that metals on the left side of the periodic table here are less likely to gain electrons and more likely to lose, whereas your non-metals up here are more likely to gain electrons and less likely to lose. So that brings us to our trend. Make sure you get this down, that as you proceed left to right across the periodic table, your electron affinity is going to get higher. And as you go down a group, your electron affinity is going to decrease. So make sure you have that. If you do look closer at the periodic table trend of electron affinity, you're going to notice some trend anomalies. Now, why that happens is really due to the structure and the placement of those electrons. Any trend anomalies are due to repulsive forces in orbitals due to size of an atom and distribution of electrons. And the example that we can see here, if we look at the orbital notation for nitrogen versus carbon, you can see that trend-wise, nitrogen should have a higher electron affinity, but yet it doesn't. So why is nitrogen less likely to pick up an electron than, let's say, carbon is based on energy changes? Well, if we go here, we can see that nitrogen has a half-filled 2p sublevel. So each orbital has one electron that's in it, and as a result, you know that that is a more stable configuration. So it is less desirable to take an electron and stick it back in here and disrupt the stability. Whereas something like carbon would be very excited, and I don't mean like atomic emission spectra, but I mean would be thrilled to death to pick up an electron, putting it here, giving it a half-filled orbital, which increases its stability. Now that we've finished with electron affinity, let's close this video out talking about 3 minor trends that you still have to know about and understand, but don't make as prevalent an appearance as the rest that we have done. Let's go through metallic character, non-metallic character, and reactivity. So here, we're going to start talking about metallic character, and of course, featured on this slide is the mighty Rob Halford of Judas Priest. This is Bruce Dickinson of Iron Maiden, and of course we have the metal horns up. Well, metallic character isn't so much about this as it is how much an atom will have properties that resemble that of a metal. And you guys can have a reminder, properties of metals are good conductors, ductile, malleable, hard, shiny, but the most important thing when we talk about metallic character is how likely an atom is to lose an electron, which is a property that all metals have. When we look at this, you guys should know that metallic character is going to increase as we go right to left on the periodic table. So that, as you guys know, is where all of your metals are, right? We have your alkali metals, alkaline earth metals, and transition metals. And of course, metallic character is going to increase down a group. So let's think about this in terms of structure. How will structure help dictate this property? Well, going down a group, you guys know you have the Auger postulate, which says every time you go into a new period, you have effectively added a principal energy level. The electrons are now further away from the nucleus and therefore less attracted to the nucleus, which is indeed also the girlfriend postulate, making it more likely that they will be lost. Tying in some of the trends we've seen already, you guys know metals that are in the lower left-hand side have the lowest ionization energy, lowest electron affinity, lowest electronegativity, largest radius, which of course will make them more likely to lose electrons. And when we want to know why the metallic character is going to increase right to left, well, that's because the nuclear charge winds up decreasing. The lowest nuclear charges in a period are over here, whereas the highest ones are over here. Important for us to understand that the lower your nuclear charge is and the less effective it is, the less likely you are to gain electrons and the more likely you are to lose, which explains metallic character. Non-metallic character is the opposite of metallic character. Non-metallic character will describe how much an element's properties will resemble those of a non-metal. And you guys know non-metal properties are brittle, dull, soft, poor conductors, but most importantly, your non-metals are the gainers of electrons. So when we want to talk about quantifying non-metallic character, you can look at how likely some element is to gain electrons and say if you are likely to gain electrons, you have high metallic character. How does structure dictate the non-metallic property? Well, by this point, you should be pretty familiar with it. Basically, non-metallic character will increase as you go left to right across a periodic table. You know at your left, you have your metals, and as you go right, you have your non-metals. So the further right something is, the greater the non-metallic character is. And why that is due to the fact that going left to right across a period will have your nuclear charge increasing, making the likelihood of gaining electrons greater. When you go down a group, your non-metallic character will indeed decrease, and that is due to increased electron shielding, valence electrons being further away from the nucleus, the addition of a principal energy level with each subsequent period you go down, which we know is the Auger postulate and the girlfriend postulate at work. So a hint for you guys will be the higher your ionization energy and electron affinity, the greater your non-metallic character will be. Here is a visual for you guys that show metallic character and non-metallic character. Make sure you get this summary down in your notes. Okay, the last trend we're going to talk about is reactivity. And we've talked about this a little bit as we've gone through this unit, but now we are officially throwing it at you. Basically, reactivity is a relative measure of the ease that an element will engage in a reaction by either gaining or losing electrons. It is important to make a note that reactivity for metals and nonmetals are opposite one another and different. So metals will be more reactive at the bottom of your group and the further left you are, whereas the further right you are for a nonmetal and the further at the top of the group you are, the more reactive you'll be for a nonmetal. So in terms of your most reactive elements, francium is the most reactive nonmetal because it is further down and to the left, whereas fluorine is the most reactive nonmetal because it is further up and the farthest right. One way to remember this trend in reactivity is to consider the more electronegative and the greater your electron affinity is, the more reactive your nonmetals will be. If you are a metal, more reactive metals have lower ionization energy and larger radii. So recapping reactivity, more likely something is to engage in a reaction, the more reactive we will say it is. So in summary, here are all your periodic trends at a glance. Make sure you label your periodic table with the information that is coming on these slides. All right, that does it for me with our lesson on periodic trends. Part 2 of this video comes to a close. Make sure if you guys have any burning questions on anything such as how structure dictates the properties you just learned about, you bring it to the burning questions segment during the next time we convene. It has been a pleasure taking you through periodic trends. I will see you soon on the flip side. Peace out.
That's all, folks.